morning. This is where we left off on Tuesday, right? So we already decided the form of each parameterization. And now the goal is to simply find that function f of t that would satisfy the given conditions. So we're told R0 has to equal 4, 1, 1, but we also know what R of t equals. So that has to equal 4, 1, 1. Right? That means that this piece here has to be the 0 vector, right? Which means that has to be 0. So make f of t a number times t. Now R of 8. So it has to be 9, negative 3, 3. With f of t now being n times t, f of 8 would be 8 times n. Let's find that n. Subtract that 4, 1, 1 vector from both sides. Find negative 3, 3 minus the 4, 1, 1. Four, 3 minus 1. Eight n would have to be 1. And so n is 1 over 8. That'll be the parameterization for these conditions. And now R of 6 has to represent the point P. R of 10 has to represent the point Q. There we go. Oh, I didn't bring this along with me. So let's bring that back up for our reference. So if R of 6 is representing P, then R of 6 would just equal the vector 4, 1, 1. Which again, you should be able to see f of 6 would have to be 0. Six minus 6 is 0, so let f of t be t minus 6 times some number n. Right. We'll use the R of 10 condition to find that n. For n would have to be 1. So n would have to be a quarter. And so that would be the parameterization to satisfy these two conditions.
Would you get the 6 negative 2 negative 3?
The what vector?
In solving for our
Making fun of my handwriting? Yeah, it's okay, you can. Just remember that when I'm grading your quiz. And we have that one last condition. Oh. All right, so now P and Q correspond to the values t equals 0 and t equals -2, respectively. Well, this is the same as part A. So it's going to use that same conclusion. F of 0 has to be 0, so we're going to say f of t is just some number times t. But now r of -2 is the second condition. Using the results of part B, we know that -2n is going to have to be 1. So n in this case will have to be -1/2. I'll write it up here this time. That parameterization would satisfy this condition. keep in mind, all three are the same line. We're just now deciding how do we want to define what we multiply that second vector by to guarantee the specific value of t representing this specific point. But they're still all the same line. All right. It's not on here. The case where f of t equals t is the default case. That's where you always let 0 represent your initial point, your p, and 1 would represent your q, so that if you just let t go from 0 to 1, it's just the line segment PQ. Point of this question was to show that that doesn't have to be the case. So parameterize the curve x equals negative 5z squared in the xz plane. All right, so this curve is strictly in the xz plane. And we want to find a parameterization for it. No need to overthink this. There, tell us what x equals. Let z be your parameter, call it t. X would then be negative 5t squared. We just said z is t. What's y?
0.
0. Why?
Depends on the game.
Because it's in the xz plane. What's the domain for t? For everything. There's your parameterization of the curve. Being able to parameterize a curve is going to be extremely important when we study line integrals. Let's evaluate some limits. Remember, evaluating the limit of a vector is just finding the limit of each component. Let's look at it component by component. What is that first limit? What is it? You're close. It's what? It's just 2. You were doing derivative. That's the composite function theorem, which says as long as your function, in this case e to the t, is continuous, at that point, whatever you're approaching, then you can pull the limit inside the function. So it's e to the limit as t approaches 0 of t, which is 0. 2e to the 0, 2 times 1. That's what allows us to do basic substitution for any function. What's that limit? Hmm? Not 1.
-1.
It's -1. How'd you get it?
I have to do one time because it's 0. I got to shift it to the top and bottom, and then I plug in negative cosine. Then it's like negative cosine and 0, and then that's negative.
You did more work than necessary. You don't have to use L'Hopital. You can. You don't have to. Remember that special limit from Calc 1 proved using squeeze theorem? Just multiply your denominator by negative, which means you multiply the overall result by negative. That limit's 1. -1 times 1 is -1. And what is that limit? -1. That's polynomial, so just direct substitution works. So that's our limit. Two, -1, -1. I guess that one was easy. It's never reassuring when buildings creak that much because of a little bit of snow. And we're on the 2nd floor, so we're screwed. At least on the 3rd floor, we're pretty safe. We'll just fall. 2nd floor, we're going to get crushed and then fall. What's that limit? What is it? You tell me, is it? You think. All right, you're in Vegas, except you're betting your grade. How much would you wager? Well, that's not good. No confidence in your own answer. And this is why the house always wins. Shame, you're right, it is 0. E to the -2t, isn't that the same as 1 over e to the 2t? What happens to 2t as t as t goes to infinity? What happens to e as you raise it to a much larger power? It's also going to keep getting larger. What's 1 over a larger and larger number? 0. What's that limit? 2/3. Yeah, that one's fairly obvious. L'Hopital's quick application of L'Hopital's rule. I just prefer to look at, you have a linear function over a linear function. They increase at the same rate. So you just look at the leading coefficients. I don't need the parentheses. What about that one? Hmm? I think I see how you got it. That's not a reciprocal tangent. That's an inverse tangent. Hmm?
Undefined.
This limit is defined. So what does 2t do as t goes to infinity? It's going to infinity. So what we're saying is limit as u approaches infinity, inverse tangent of u. It's pi over 2. Tangent approaches infinity as x approaches pi over 2. Remember, we're also only looking at minus pi over 2 to pi over 2, because that's the range of inverse tangent. There's our limit. What's that limit? That was easy. That was boring. What is that limit? How'd you get it?
Zero and that in the term plus.
So you use L'Hopital's again.
Yeah.
Which is typically the default. Or you could also factor t minus 4. Isn't t minus 4 a difference of squares? Root t plus 2 times root t minus 2. Your root t minus 2's cancel. Right? And they can cancel because since t is approaching 4, t will never be 4, which means that will never be 0 over 0. And you're left with just root t plus 2, 1 over root t plus 2. There's your 1/4. Oh, another easy one. What's that limit? Sound more confident. This is just a basic substitution. All right, so there's that limit. So we're going to need to review Calc 1 if necessary. Because that was all just basically Calc 1, wasn't it? There's nothing new there. Derivative of vector valued functions. What was the definition of a derivative of a function?
Rate of change of the output with respect to a small change in the input. Very small change.
That is still technically an average rate of change,
Infinitely small.
not a derivative. And I would agree that one interpretation of the derivative is a rate of change, but that wasn't how it was defined.
So it had a given point.
Again, interpretation, not the actual definition.
So when it has h approaches 0, f of x minus h minus f of x over h.
So close. And I won't use h here to keep in line with the definition. I'm going to use delta x. That just means the same thing. H just means an incremental change. Some texts actually do use delta x instead of h. It was plus, not minus. Now, again, that's actually the derivative function. Right? The derivative is a constant. So you just replace x with a number. Well, how do we think derivative of a vector is going to be defined?
It's still a vector, but the derivative with respect to t of each component.
So you jumped ahead. That's actually how we're going to evaluate it.
It's the derivative of each component.
So that's how it's evaluated. Definition is the same except we replace f with r. And remember the two notations? That's actually two of the three notations for derivative. Trivia. You know what that notation is referred to as?
Radius.
Yeah. Do you know why?
He's the one that would use that notation.
That's true. Actually, is it? I have to review that history. But there's a reason why he's credited in calculus.
He invented my primary.
He wrote the paper on calculus first. Newton's was published. Why? It's actually a really sad story. The society responsible for publishing papers, the president was Newton. Corruption at its finest. So Newton actually, I don't want to say stole, because the two papers were written independently, but he kind of stole the glory, because Newton's paper was submitted after Leibniz's, or Leibniz's, however it's pronounced. It's not about what you know, it's about who you know.
Is everything we learn?
Huh?
Is everything we learn?
No, well, depends on what you learned.
So it is true, it's not true.
But I mean, Newton did write a paper on calculus. It's just wasn't submitted before. Wasn't the first submitted. Einstein stole the idea for general relativity. He was working in the patent office. A lot of stuff is credited to not the person who actually came up with it first. Then we have, of course, the prime notation, which you're all familiar with. There is a variation of prime notation. Used extensively in physics. And you'll probably see me use it a lot. Dot notation. We use dots instead of primes to represent derivative with respect to time. And there is a third notation that is not really commonly used until differential equations.
Multiply both sides by its normal product.
Well, that is differentials. So that's something different. So the D notation. Capital D with a subscript represents derivative with respect to. That notation is especially useful if you look at the derivative as an operator. Then that would be your operator, D. And then as already mentioned, that's just the limit. We know how to find the limit of a vector valued function. So when we actually go to compute derivatives of vector functions, it's just derivative of each component. Oh, but what was each component of a vector valued function again?
The real value.
They're just real valued functions, aren't they? When did you study derivatives of real valued functions? Calc 1. Oh, okay, well then this is just Calc 1 all over again. So still nothing new. Isn't that lovely? And since each component's a real valued function, that means all of your derivative rules from Calc 1 are still valid. What were they? Let's list them off. So chain rule, most important rule. Product rule. Quotient. I'll give that exponential, derivative of exponential function. Power rule. Your logarithmic rules, derivative log function, your trig rules, inverse trig, and the inverse trig rules. And there's one other, scalar multiple rule. Well, let's try and extend those rules, not to just the individual components, but to just the entire vector overall. So R and U are differentiable functions, or differentiable vector functions. F is a differentiable real valued function, or I'll probably just refer to it as a scalar function. And let C be a scalar. Well, scalar multiple rule is the same. Multiply a vector by a scalar and take its derivative. It's just the scalar times the derivative of the vector. That shouldn't be too difficult to prove. Then you have your sum difference rule, which is again the same. Take the derivative of a sum or difference of vectors. It's just the sum or difference of the derivative of the vectors. Oh. How many types of products do we have for vectors?
Two. Three.
3. What are they?
Cross.
Dot product, cross, and multiplication with a scalar. That means we have 3 product rules for vectors. You have your scalar product rule. Because now the scalar doesn't have to be a number, it can now be a function as well. Well, that kind of looks just like product rule, right? Then you have the dot product, which again looks exactly how you would expect it to look. And then you have the cross product, which again looks how you would expect it to look. Are we going to have a quotient rule?
No.
No. Quotient of vectors is not an actual operation. Oh, good. Quotient rule was always the worst. Chain rule. Again, exactly what you would expect. Now, it's important to note that these 6 properties, you don't actually need any of them.
What do you mean?
So glad you asked. I'll use property 5, for instance. Couldn't I just take the cross product of the vectors first, then take the derivative? So then why would I do 2 cross products when I can just do 1? In every single case, you can just perform the vector operation first and then take the derivative of the result instead of trying to use one of these rules. Again, chain rule, just evaluate the vector over the scalar function first and then take the derivative. which is typically what I do. I don't actually ever use any of these properties. Only in theory do these properties play a role. There is one interesting property, though. If a vector dot itself is a scalar, then the vector dot its derivative is 0. And by scalar, I mean a constant. Right, so when you take a dot product of vector functions, it's going to be a function. Right, because C is a function. But if it's not dependent on T, right, so it is just constant, then that vector is perpendicular with its derivative. That's what this property says. I'll let you prove it. I don't think I'm going to use it in that spot. So I'm definitely not going to be using this in this set of slides, but it will be used later, and it is actually a fairly important concept. If you look at R prime, when you think of derivatives, you think of, you said it, tangents, right? Tangent line. So wouldn't R prime give a direction vector for a tangent line at a point? So again, you theoretically have an infinite number of tangent vectors. You'd only have two possible directions, right? Same direction as R or the complete opposite direction as R. But any magnitude would work. But we want one specific one. It's called the principal unit tangent vector, or just simply the unit tangent vector. And it's found how you would expect. It's R prime over the magnitude of R prime. And the unit tangent is represented as a capital T. So a bit of notation. Can we write this Do those say the same thing?
No,
I heard you first. The left-hand side is what?
the magnitude,
Of
the derivatives,
what's the right-hand side?
the derivative itself.
It's a
The
derivative of
direction.
itself, right? What does itself mean?
The derivative itself. Just the derivative.
I also heard you say no. You agree with the left-hand side?
Yeah.
What about the right-hand side?
It's just the derivative.
So what did...
difference is that the one on the right has a direction.
Okay, so look at how it was written. Is that R a vector on the right? So what does just R represent?
The magnitude.
Oops. Oops, again, not derivative. So that one on the left, I do agree, it's the magnitude of the tangent vector. That one on the right, though, that's the derivative of the magnitude. Right? You find the magnitude of R first and then take its derivative. Versus taking the derivative first and then finding the magnitude. They are not necessarily the same thing. So you cannot use that notation. Generally speaking, they are two different things. Now, when we get to physics and motion, there is a way around that. But we'll discuss that when it becomes necessary. Which I think is after the exam when we study motion in space. Integration. Does anyone remember the definition of an integral?
The assigned area between function and the x-axis over a given interval.
So that is its interpretation. Right, so yes, the integral does give you a signed area. That's not the formal definition. And I wouldn't be surprised if you don't remember it.
The sum of
the function increase in height if you have these small steps divided by the size of the steps.
You're getting there.
The limit as h approaches 0 there.
It's definitely a limit, yes. It's the limit of the Riemann sum, or of a Riemann sum, because there's theoretically an infinite number of them. Which sadly, a lot of people do not cover in Calc 1 anymore. The Riemann sums kind of just disappeared into the void, which is an absolute shame. If you take real analysis 2, you'll be examining Riemann sums way more in depth. I think you might actually even do it in real 1. Undergrad. Grad level is just, never mind grad real 2. And this is typically how it's written, because there is no one set Riemann sum. So to form a Riemann sum, you need obviously the function. You need a set of points called C, and you need a partition of the interval called P. So you partition your interval, you choose a point from each partition, sum F at each of those points. That's a Riemann sum. Or I'm sorry, it's the Riemann sum is the sum of the function evaluated at each of the points times the length of that partition. Then you pass that through a limit as the norm of the partition goes to 0. Norm of the partition is defined to be the length of the largest partition. In the case where each partition has the same length, or each subinterval in the partition has the same length, we then say that the partition is regular. And in Calc 1, if you studied it, you studied 3 special Riemann sums: right endpoint, left endpoint, and midpoint.
What about trapezoidal?
Those are numerical approximations. Those, while they are technically Riemann sums, they're not studied in Calc 1. They're studied in Calc 2. Typically, they're not. So you went a little more advanced in your Calc 1, which is fine because there's also Simpsons, which is also a Riemann sum. And it doesn't matter the Riemann sum because all of them converge to the same value, and that is the integral. Yeah, well, Riemann sums are a bit of a pain in the ass when dealing with vectors. And in fact, that kind of study is well beyond the scope of a typical Calc 3 course. So we just take as the definition the way to evaluate it. So you have your antiderivative. That one's fairly straightforward. It's the antiderivative of each component. So antiderivative is the correct terminology, not improper integral. Again, integral has a specific meaning. It is a constant. And then we have integration itself. This is where we take as the definition how it's evaluated. It's just the integral of each component. All right, so if you wanted to be really mathematically correct, you'd set up a Riemann sum for each of the three component functions and then take it through a limit. And how do we evaluate integrals? In Calc 1?
What do you mean how do you
How was it evaluated? What was the method called? It has a name, and it was the whole point of Calc 1, actually. Fundamental theorem of calculus, specifically, I think it's part 2. All right, it says you find an antiderivative of the function, call that antiderivative big F, and then it's just big F of B minus big F of A. Fundamental part 1 relates derivatives and antiderivatives. Right, part 1 basically says that the antiderivative is the opposite of a derivative. I'm sorry, no, it relates integrals to antiderivatives. Right, tomorrow we will do the problems. Let's see, do you have a homework due tomorrow? Also, don't forget your initial posts are due tonight. Next Friday is your first exam. Keep that in mind. See you tomorrow.